What's up, YouTube? Welcome back, Happy New Year. And yeah, I have some updates to this Tesla call, and I thought I wanna make a new video for you guys because there were some questions about it and I changed many things over the time. So I just wanted to show it to you guys so you are staying updated on this project. So many things have changed. So now I got two GU81M tubes in it to push way more current, or the double of the current that I normally push in this application. So I had to change some things. So in previous videos I changed the power supply to two microwave oven transformers in parallel, so they pushing together around 4 kilovolts with the voltage doubler, and yeah, they are being able to push the right current these tubes need without breaking down the voltage too much. So, but the most change, or the biggest change for the application with the two tubes, is the primary. So yeah, I experimented a lot with it because the old primary had a really big inductance, so the resistance at the working frequency was really high and this primary was not able to push enough current, so the output got not really much bigger with a second tube. So now I changed the primary, got less windings, and I spaced the windings a bit. They have about I think 3.6 millimeter spacing from them. So also the tank caps, or I got a bigger capacity on the tank, obviously because I changed the primary. So, and I added a sort of soft start. It's just a relay. This just switches on with the power when I switch on the Tesla coil, but only the mechanical delay is preventing the transformers to suck about, I don't know, 30-40 amps of switch on current. So this needs a while to switch on, about some milliseconds, and I think that the sinus wave of the mains in this little short time will go to the negative or whatever. It just works. So sorry, I'm not so big in theory. So, but I'm now able to just bridge the ballast transformer, and I can run this application in full power now without popping the breakers every time. Yeah, there I have a schematic I want to show you later. Yeah, but the secondary stays the same. The grid feedback circuit changed a little bit. I'm still experimenting with it. Now I have a combination of resistors. It's 1 kilo ohms and a tungsten lamp with 75 watts on 230 volts. And yeah, I just tried a little bit around, fiddled a little bit around. There I had the idea to separate the grids a little bit. That's grid 3 of the tube with a 50 ohms resistor, but I don't even know, or I don't even can say if this prevents it from oscillating or something else. Normally when tubes getting in parallel, you have to separate them with resistors a little bit. I know that out of tube amplifiers in audio or musical for instruments applications there. When you look at schematics, they separate them with resistors, I think, to prevent them from oscillating together, or yeah, whatever. So the resistor and capacitors for the grid 3 stays the same. I'll show you that soon on the schematics. Yeah, but I'm running into new problems with this application with the two tubes, because I draw a lot of current. So on full power, without the staccato mode, I draw around 20 amps from the power line. So that's a lot. And that's way too much for these transformers, so they overheat really quickly. So I think after 2 or 3 minutes they're getting over 100 degrees hot. You can't touch them. That's really bad for these transformers, and that's a big problem. Also, the secondary gets really hot really fast. So after about 2 minutes too, it's getting about 60 degrees. So the primary stays around 40 degrees. The capacitors warming up too, but not too badly. Yeah, tubes are getting driven really hard in this application. So now I decided to change something. So that's because I make this video. I want to show you how it is yet, because I will change something. I will apply these in series at the secondary coil. So instead of 4 kilovolts, these were with a voltage doubler. Instead of 4 kilovolts with a voltage doubler, they were then pushing 8 kilovolts. I don't know how much it is under load. I think much less, but around 8 kilovolt with a voltage doubler. So then I have to change something in the wiring, and I think I have to change something in the feedback. Whatever, I will find it out soon. So that's because I draw a schematic for you, now that you've seen how it is now, because it never will stay the same. I just want to show you how it is performing now. Funny thing is, I tried it before I take the video. Now today it's a little bit colder, or the air is a little bit different, and I have to use today the bigger top load, because it won't work right with the smaller top load. Yesterday it was different. It wasn't work right with the big top load. It works better with the small top load. So that's a good example how unstable such VTTCs can be. Yeah, but okay, it works now okay. Yeah, I just show you that. So switch it on. Also, the arcs are today a little bit bigger with this top load. And really crunchy. Okay, that's cool. So full power. now you can see there is a big current going on in this circuit. These arcs are really thick and bright. So I let it run a little bit, so I have I can measure the temperature after that on the secondary and on the capacitors and transformers, so you can see how hot the stuff is getting. The tubes are okay, getting a slightly red. Today my staccato won't work right. That's really crazy. Yeah, that happens. Okay, I would say it's enough. So we can measure the temperatures. So I have this thing. So let's see. Oh, we are already at over 90 degrees on the transformer, on the primary winding. I can smell it. So it's really cold here where I am. So I think the normal temperature here, yeah, 30 degrees. So what we have here on the caps. Well, today these are getting a good temperature. What can we measure? The grid. Resistor, well, that's okay. 50 degrees, it's not hot. The tube. No, I can't measure it right. Yeah. We have the secondary. What do we have here? Well, sometimes when I get it right, 45 degrees. Yeah, it's just okay. But you can see these transformers are absolutely on their limit. That's really bad. No. Where are the high temperatures? Oh, there we are. Yeah, already cooling down. What do we have here on the heater supply? Well, it's just good. This transformer also pushing alone these two tubes on the heaters. So this thing has yeah, enough power. That's nice. There we have the schematics. We start with the power section. So there we have my artful soft start. It's just a relay that bridging the 7.5 ohms resistor and just delays a little bit the hard on switching, so this prevents the circuit of drawing instantly how much amps and popping the breakers. So this just works good, I have to say. So there we have the ballast transformer. I'm now on full power mode. So when I want to have less power, I got higher with the inductivity and the voltage will drop. So we have the two microwave oven transformers in parallel on the primary and secondary to push high currents on about 4 kilovolts after the voltage doubler. So in the voltage doubler circuit I have 8 pieces of microwave oven caps. These are about, sometimes some of these caps are 0.95 microfarads, some of them are 1.15, I think. So, but it's around 8 microfarad on 2100 volts. So the diodes I'm using are the 1N5408 diodes. These are 1 kilovolt diodes at a rating of 3 amps, and I have 26 of them in series for the voltage doubler, or the one-way man, my English. On the one-way rectifier. So sorry. There we have the cap that is just there to save the power section a little bit from the RF current. So, and there we go out with 4 kilovolts at, I don't know how many amps, 2 amps, whatever. So there we have the rest of the circuit. So we came in with the 4 kilovolts into the primary circuit. So there's the tank cap with about 1.8 nanofarad at 30 kilovolts. It's actually a little bit more. I measured it and it was 1.97, I think, when I'm right. I don't remember right. Yeah, the primary has 28 turns with 1.32 millimeter diameter wire. The space between the wire is 3.6 millimeters primary diameter. So the thickness here is 125 millimeters. So we go down. Oh, I actually missed the specifications of the resistors. So these are 50 ohms resistors wound around with 1 millimeter wire, 70 turns each, to prevent the tube of high frequency oscillating. There we have the grid 3 resistors. These are these guys here. So network goes to here. That's the feedback network for the G3. And there we have G1 and 2 of these tubes tied together, and from these tubes in parallel, and they have their own network with a tungsten lamp. So there we have the feedback. That's 15 turns, 1 millimeter diameter wire, just slightly under the primary. It's about 5 millimeter under the primary. So this works just good. And there we have the secondary with 30 centimeters or 300 millimeters wound with 0.4 millimeter wire, about 680 turns at 75 millimeter diameter tubing. So I experimented a little bit with top loads. I have 3 top loads here and a 4th one which I can switch aluminium plates to tune it right. Now what is working the best is a top load with 40 millimeter height and 160 millimeter width. And other applications with a little bit more turns on the primary, my bigger top load works really good actually. The arcs are a little bit longer than with the small top load, but I have the feeling with the small top load and the primary like it is now, this all will work a little bit more efficient. So that's because I leave it like it is. Yeah, so I think that's it for this video. When you have questions, please write something to me. I will answer to you. Then bye bye.